Hello.
哎，佳宇，
哎，Hello，肥哥。哎，Morning。
差点搞错了，我靠！
啊，对，那边那个 Chase 那边那个 conference chair 每天都在跟我说让我去待一天。啊，
你说那个 Chase 是吧？
是
OK
是我，哎，真是太难了。我们这原来还有当天往返的飞机，现在没有了。
I see。
OK，明白。哎，Hello，贾瑞。Oh yeah, that's right. That's right. I was just wondering. So we start at 8:15, right? And then how much time do I have? 45 minutes? 50 minutes? I have 1 hour. Okay. All right. Okay. All right. All right. So I have around 1 hour. Yeah. 9:30. Okay. Okay. That's great. All right. I'll try not to do that. Yeah. Even though I do that pretty often.
Yeah.
Hey, hello, Hongzhou.
Hey, how are you?
I'm doing good. How are you?
Good. I'm going to introduce both of you first.
Oh, okay. All right.
Before we start.
Cool. Let me try sharing my screen.
Yeah, you can share your screen.
Okay. Yeah, I'll see if I can do this slideshow. Do you see this screen? Okay.
Yeah.
Okay, that's cool.
And good morning or good night, everyone. It's my great pleasure to introduce the two speakers today. And our key speakers is the Dr. Jiayu Zhou. And Jiayu is the current associate professor in the Department of Computer Science and Engineer at the Michigan State University. He received his PhD degree in computer science from Arizona State University in 2014. And Dr. Zhou has a broad interest in large-scale machine learning, data mining, biomedical informatics with a focus on transfer and multitask learning. His research has been funded by ANZF, NIH, and Office of Naval Research, and published more than 100 peer-reviewed journal and conference papers in data mining and machine learning. And Dr. Zhou is a recipient of NSF Career Award in 2018. His paper received the Best Student Paper Award in 2014 IEEE International Conference on Data Mining, and the Best Student Paper Award at the 2016 ISBI, and the Best Paper Award in 2016 IEEE International Big Data. Our second discussant is the Dr. Fei Wang. Fei Wang is an associate professor in the Division of the Health Informatics, Department of Population Health Science, Cornell Medicine, Cornell University. He got his PhD from the Tsinghua University in 2008. He's a recipient of a National Exceptional Excellent Doctoral Thesis Award. Dr. Wang's current major interest is AI for health data science. He published close to 300 papers on top journals and also the conferences such as ICDM, KDD, and many other journals. His paper has received lots of citations so far, and his papers has won 8 Best Paper Awards in the top conferences on data mining and medical informatics. And I think now is your turn, Jiayu.
Oh, thank you, Dr. Zhou, for the very detailed introduction of both of me and Dr. Wang. Yeah, it's my pleasure to give the presentation today about my research on the neurodegenerative diseases. Right, so I have a very detailed bio just presented by Dr. Zhou, so I'll just skip that. So first, I'm going to briefly talk about what we do in our lab. So I'm from Alden Lab from Michigan State. So what we do is all of the research we have been doing are surrounded by this y equals fx, right? So we give an input, we're trying to model this function, and give an output. It can be classification, where we're trying to classify into different categories, and it could be a regression problem where we're trying to predict like the stock price and things like that. And it could also be the reinforcement learning where we give the stats, X is our states, and we're trying to predict the action we're trying to do, right? So all of things are surrounded by building this tiny little FX. And what we do is, typically we have we collect a bunch of training data, and we have this learning procedure, and we're trying to model this F and trying to infer this F. And in a lot of domains that we've been working on, we also have this domain knowledge, right? So if we're working on this bioinformatics, and especially in some kind of domain where you have a lot of knowledge that not in the form of your training data, and it could be very helpful if we can design specific learning algorithms and models that can integrate this kind of knowledge, and we're trying to learn better F, right? And then we focus on different aspects of F. So we start with the performance, or what we call generalization performance of that, which means we're trying to build an F in a training data, and then we're trying to have this F to perform as good as as possible in the data we haven't seen before, the testing data, and so usually there are kind of some kind of like distributional differences between your training and testing. So in the generalization, you probably have to consider about this and consider all kinds of bias, for example, and then you trying to build this kind of learning algorithm that can be robust against this. And the second direction we have is more recently we consider about other aspects other than the performance itself, right? So we consider the privacy, we consider the robustness and fairness. All of are secondary, I'll say secondary properties that are other than predictive performance we consider. And I'll also consider about this interpretability of the model where really we build a model, we're trying to explain to people what we got in our FX and why it's building this, it's making this prediction, right? So this is, I think it's the important part for human to trust this AI systems, why you're making this prediction and what makes you make a prediction, right? So yeah, so for the generalization, basically what we do is we, as we just mentioned, we're trying to integrate different type of knowledge, right? So for example, we do this transfer and multitask learning typically in a scenario where we have multiple learning, either domains or learning tasks, right? So by learning tasks, meaning one classification task is a task, right? And then we have multiple related this classification or regression problems, and we're trying to simply borrow information from other learning tasks to help us. So that's knowledge from learning. And then also sometimes we have this data knowledge, right? So if we have multiple type of data and some of the data may not be directly used, and so so we can, trying to do some kind of knowledge fusion, data fusion from different sources or modalities, trying to bring this information together to make a prediction. And then also we have this from the domain knowledge where we're trying to revise our objective function or trying to formulate in different ways so we can during the learning process, those knowledge can really be guiding us to, let's say, a region where the solution are better in terms of the quality. And also we do a lot of like missing data, noisy data, and trying to be robust against those. And then second direction, the robustness, as some of you may be very familiar with, right? So if we're dealing with this kind of deep neural network, especially, let's say, for example, we have a toy example here where, you see those are, a decision surface, decision hyperplane of a neural network. So we have this kind of positive region and have negative region, and then all those training data points are sitting over here. And then, if you take a look at this decision boundary, right? So you find out that some of the data points are sitting really near the decision boundary. Right? And then if you search through this decision boundary, there are chances that you can find one of the spots, right? And then if it's, let's say if it's medical imaging, for example, right? And so if you find a spot, meaning that you actually find imaging we use for training, and then it could be very risky stuff, so you actually have people stealing training data from you, from your training, from your model. So there are things trying to prevent when you're trying to build the model and trying to release the model, and so people won't steal training data from you, right? And then and then we can actually use this kind of property to protect, to discover something in our data as well, right? So typically when this happens, means some kind of overfitting and some kind of some kind of smoothing you can do for your model as well, and also interpretability. And we're trying to bring as much information as possible for the predictive information for people to know that what's making this prediction and what's inside our data. And when a couple of years ago, we also built this human in the loop type of learning systems where we really trying to have this expert be involved in the learning process to provide this guidance along the way when you're doing the actual learning. So yeah, that's the three direction we have, and we have applied this in quite a bit of applications. I would say one of the major things we do is we're trying to use them for neurodegenerative diseases, and we have also applied our machine learning algorithms we develop in a lot of different areas. We say, for example, medical informatics, and more recently we have this kind of molecular studies and we're trying to discover drug signatures and then provide some kind of treatment as well. And we used to work on a lot of the traffic informatics as well, and limnology. So today I'm going to mainly focus on this neurodegenerative diseases, right? So for some of you who don't know about that, I don't know if you have seen this movie before. It was Still Alice. It's an Oscar movie, and back in 2014. I've been working on Alzheimer's for last, I would say, 10 years, right? So that means, even it's more than 10 years. Yeah, so that means that when I was still a PhD, I'm working on this Alzheimer's, right? So by then, my advisor got a grant on the Alzheimer's, and I work on it. And you may be curious what makes me to work for so long, right? So in fact, 2014, I graduated, and I was working in the Bay Area and as a research engineer, where I do a lot of like recommender system, trying to do compress this kind of deep neural network, trying to do this recommender system in mobile devices. I do a lot of fancy stuff, right, back then. And then people would say, hey, why are you doing this kind of Alzheimer's? Kind of boring, right? But the thing is that really, this movie is part of the thing that actually changed my, I would say, career goal, right? So you see that, people are suffering from different types of disease, and really there's something that you can do. Your expertise can actually contribute on that. So about 2014, this movie actually moves me a lot, and then saying why not just go back to academia, and then before I had a chance, and before I still when I still had a chance, and I'll just go back to academia and then continue working on this thing. And I find a lot of more exciting problems to work on it. So today I'm going to share with you some of them. So what is Alzheimer's? So when we talk about neurodegenerative diseases, typically refer to a couple of diseases, one of them being dementia, right? And then today we're going to focus on dementia, right? So one major type of dementia is called Alzheimer's, and then it comes with a lot of symptoms. We typically pretty well-known symptoms, right? Including memory loss, communication and language issues, and lack of capability to focus and pay attention, and reasoning and judgment, and in the end, people will lose this vision as well. So seems pretty okay, I would say, as compared to cancer and stuff. But let me tell you why. It's much worse than cancer, and the thing is that it lasts longer, and then at the end age of that, it'll bring huge pain to the patient and the people who surround the patients, right? So the care is pretty costly, and then you cannot take care of yourself, and that's pretty bad. And then what makes things worse is that we don't actually have that many ways to stop it, slow it, or prevent this disease, right? There are a lot of failed clinical trials. We know that a lot of good news, and that turn out to be not that effective later on, right? So so there's been a lot of efforts, right? And then and still we need more efforts to actually help on this. And then for those of you who don't know this, this in our brain, we have this connecting neurons, right? And then one of hypothetical pathology of this Alzheimer's is that we have those kind of plaques and forming in the brain, and then that is cutting down the connection between your neurons, and then your neuron is, lack of nutrition is kind of that, and they become part of the plaque, and then it's going to continue killing more and more brain cells, right? So that's why that's one of the hypotheses. There are a couple of hypotheses behind it. And then it's actually the 6th leading cause of death in the United States by 2021. And before that, it was 5. And that who is jumping like before this, right? And then the main issue of Alzheimer's is people are going to live through this years of morbidity, and this is really pain. And then internationally, we'll see like around 100 million people are going to be affected by this by the end of 2050, right? So that's going to be a lot of them, a lot of people. So it's a direction that NIH has put a lot of efforts, and then we're fortunate to actually join the force to tackle this kind of disease. And we're going to talk about today. We're going to talk about a couple, actually 2 research we have done on this direction. One of them is from imaging markers. This part is I would say more a supervised learning problem. So it's not like the reinforcement learning part. The reinforcement learning comes later when we talk about behavior and especially language markers of that. Okay, and then so why do we use imaging, right? So if you take a look at this kind of Alzheimer's disease progression, we start with what we call a mild cognitive impairment, where we have some part of the brain is starting to go bad, and then in this time you will have this kind of short-term memory loss, right? And then people will say, hey, I kind of forget things about pretty recently, right? Including what I've done in the morning, let's say, for example. For those of you in the evening, right? So I can't forget what I've done in the morning. And then if it's getting severe, you kind of forget like which floor I am, this kind of memory, but this pretty short-term memory. Long-term memory is fine. You can still recognize your family members. You can still recognize your friends, and you can know that a long time ago what's in your childhood. And then a couple of years after that, some people are turning to what we call mild Alzheimer's. The clock is ticking, and then 2 years, and you get moderate, and then get severe, and finally dead, right? So this is what we call progression, and then you see that different parts of the brain become bad along the way, and then we'll have different symptoms along the way as well. And then if you take a look at the brain, right? So this is brain autopsy. You'll have like the illustration of that. You'll find that the brain really changed a lot, right? And then you'll find that the normal brain is pretty rich, I would say. And then if you take a look at the right, and you'll find out the Alzheimer's brain is it's pretty smaller in terms of volume, and then you have a lot of more like ventricles or empty space inside of your brain as well. So it's easy. I'll say it's pretty easy for somebody to tell it's an Alzheimer brain and a healthy brain, right? And then that's why people are starting to work with this kind of imaging markers. We're trying to use different type of imaging to study how this disease progressed over time, right? And then we used to, so we started with the PET imaging, and then we'll have a lot of established research on how to using this kind of T1 or T3 kind of MRI imaging, and then more recently we use this DTI, it's a diffusion imaging MRI, and then trying to model, trying to see how those connections inside your brain are changing over time. Yeah, and then when it comes to imaging, people will say, hey, this is pretty good, right? Because nowadays we have a lot of very fancy ways to dealing with image, right? With the image, let's say, for example, we have to, now we can do a lot of tracking, right? So especially for those of you in China, you probably know that it's pretty powerful to actually track individual people, just recognize them and trying to recognize different components. And some of you, I believe, is working on this autonomous vehicle. So we know that we can recognize a whole bunch of things just using the camera, like the Tesla type of vehicle. And then what's building behind this is, nowadays, we usually back in the 1950s, we already have this perceptron, right? So we have this kind of neural networks, starting to grow by then. And nowadays, we know deep learning has been everywhere. People have been building this kind of fancy networks using huge amount of data, right? So and then we can do so much thing about it. Every morning I open up my browser, and you see like huge amount of new research going on in the archive, right? So it's just fantastic. And what's behind this, I would say, scenario people getting into this domain is perhaps because we have a lot of data, right? So we have 5 years ago, we have this imaging net, maybe earlier than that, right? So maybe almost 10 years ago, we have this imaging net, right? We actually built this fancy library, and then we have, around 14 million images, right? And then we can use them to actually put into our deep neural network, and we're trying to build really fancy neural networks out of that. And then we need a lot of training data. But when we're talking about Alzheimer's, it's kind of a different scenario, right? Think about that. If we're trying to build a model, trying to build a regression model, for example, to predict the disease in the future, right? So what we do is we have this different type of imaging, and we have some kind of clinical samples of, the blood samples, and, we've got a proteomics and, different type of proteins inside of inside the blood, and we have everything ready for one patient. That's fine, but how many patients do we have to build this kind of model? And then I'll show you like one example, right? So Alzheimer's disease neuroimaging initiative, ADNI, is a very famous project, right? It has two phases, three phases. But the first phase, right? So I would say, for example, we spend like 5 years, and then we have $6 million being spent on this project, right? And then guess how many samples we have? We have barely 819 samples out of the quality control and everything like that. We only have like 120 samples, right? So we have to recruit samples, we have to build everything around this patients and trying to, set up a reasonable cohort. And then we have to follow this a patient for, let's say, 5 years, and then getting high quality imaging. That's really a lot of efforts, right? And then especially when you have this in multiple institutions, right? So in the end, after all those efforts, you have how many? 19 samples, right? And that's all we have. And then you don't have this kind of 14 million samples, right? And for you to actually learn this kind of classifiers on, disease, non-disease, how, if they're gonna translate to another stage, you don't have it. So that's one of the things. But what can we do? Because a lot of machine learning algorithms are motivated from this human experience, and can we get some insight from human learning as well, right? So I can, now it's my 3-year-old now become 5-year-old. My 5-year-old actually, see, it's learning from, when she was 3-year-old, she can actually pick up new concepts from just a few examples. You don't have to feed the child with 14 million images for her to learn anything new, right? So you don't have to feel like even thousands of the imaging to tell that, hey, this is a tree, this is a lion. It's not the case. You just show him like a couple images and take her to the zoo, and she'll immediately know that it's a lion. And what we can learn from the human learning is that a lot of things we learn are not independent, right? So they are actually coupled with each other. So we have a lot of learning tasks, and then one build on each other, and then they actually, they can, when you learn something new, it's actually the process of you trying to form that concept and trying to tie into those concepts you have already learned in the past, right? And then sometimes you learn a couple of things together, and then they're actually starting to help each other. So that's why in machine learning, we develop a lot of learning paradigms where we have the transfer learning, we have we have a source domain, return domain. We're trying to adapt to that, and we also have this multitask where we're trying to learn a lot of things together, and we have more fancy stuff moving forward, right? And a couple of years ago, and that's like 5 years ago, Andrew Ng actually in Europe's conference, we're talking about the trend in the industry as well. Supervised learning has been very successful and widely applied, and the next trending topic is the transfer learning. As you see nowadays, you see this kind of zero-shot learning and few-shot learning, and especially in the NLP, right? So a lot of people are actually working on that. So so transfer learning has been a very large domain. And then in clinical side and in clinical application, especially if you don't have enough examples, this could be something that can be helpful as well. Dr. Wang and I, we've been working on this medical informatics for a while, where we applied a huge amount of just develop this transfer learning, multitask learning on this, and pretty successful. I'll give you an example of how we do that in the cognitive, predicting cognitive scores. So we have this kind of one score Y we're trying to predict, which is characterizing how good it is in terms of a cognitive status, right? Are you able to do certain kind of functions, or we're trying to have a score to characterize really how good a patient is doing, right? So in healthy, how healthy the brain is. And then, our input features are the imagings, right? Imaging features, right? So we extracted, the cortical surface, extracted some variables from your medical imaging as well. And then we're trying to put up in the vector, and then we're trying to predict this Y, okay? So that's X and Y. And then we're trying to, the thing we do is we're trying to have this prediction function. And, here we use a little bit different linear model, because the reason for that is pretty simple. Is we don't have enough data to build a deep model in the very beginning. And then we start with a linear model, right? And then because the score we're trying to predict, they have the lower bounded, right? You can't predict like less than 0. So we have applied this ReLU function as well in outside of this prediction function, right? So this prediction function looks like this. And once we have that, according to the textbook, what we can do is we can build a likelihood function, and then we can optimize the parameters by minimize that loss function, right? So that's what we do. And then if we're trying to bring information from other learning tasks, right? So let's say, for example, we have the same input where we can, we have a learning task to build different cognitive scores. And predicting each cognitive score will be one prediction task, right? And then we have different X and Y. For example, we have a set of 4 X and Y. And then what we can do is we can try to build a model that can predict them simultaneously, right? So the rationale behind it is that all of the scores, they are kind of similar to each other, not similar, but they're kind of related to each other, where they are characterizing different aspects of your brain, and then the prediction are not totally independent, right? In fact, it's if you look into if you actually look into the way they measure those scores, some of the cognitive functions are overlapping with each other. So there are we have enough reason to believe that they're not independent. And then, so we can build a model to predict them simultaneously, right, for X. So if we can build all this let's say 4 or 5 prediction tasks together, potentially they can leverage the information from each other during the learning process, right? So what we can do is, what we have done is that we're trying to create this kind of subspace, right? So when we're talking subspace, you see that if we have like each learning task, and the model is W, right? So you put all this W together, form a matrix, and then this matrix, if you assume there's a subspace, basically you assume there's so you basically assume it's a low rank matrix, and you have some kind of columns and shared this kind of coordinates, and then the tasks are located in those set of coordinates, right? So to visualize this process is that if you learn this task together, right here, one node is one learning task, the model of one learning task, right? So we visualize not just not the data, but the model, right? Each model is a point. And then when you're trying to learn them together, they're kind of creating this kind of subspace, which you'll see this yellow plane here. And then during the learning, they will just try to, the subspace is trying to drag all the tasks, trying to bias in a way that trying to drag all the tasks to that subspace. Okay, so it's not dragging the data points, it's dragging actually the model itself. It's trying to bias the model, right? So, so you see this subspace is actually learned from the set of tasks, right? So it's, it's like a distilled knowledge from all the tasks, and then we're trying to bring them together. Okay, and then it's trying to bias, so it's in a way. And then this happens in every single iteration. So you have this kind of multitask learning. So that's what's behind it. Okay, so with this kind of thing, what we can do is, we're assuming there's a subspace, and we're assuming there's a low rank structure inside of that. And then we basically, we would just basically explicitly put this W decomposition into U and V into that, into our model, right? And then we have this new loss function, and then this new loss function will be solved by either coordinate descent, or sometimes we do more fancy than that. Okay, and then the one other issue here is that computationally, if you solve this U and solve this V, and then it's going to be computationally expensive. But of course, nowadays, when people are talking about a couple of days of training experiences, this not considered as expensive that much, but still, if you're trying to build different models and trying to explore different hyperparameters, it's trying to make your algorithm as efficient as possible, right? And then you don't want to use this block coordinate descent every time, because each time you're solving like a block of variables and you do this over and over. So we actually have this some kind of fancy stuff where we just have to go through one pass of your training data, and then you can still get a very good high quality subspace, and we can prove that's the case. Okay, but that's not the that's not the focus of the talk today. But one other thing we have to mention about it is that since we're using linear model, even though we put a ReLU function there, it's still considered to be quite linear, right? And then if you have this kind of feature interaction, it cannot actually be captured in those linear models. And then there's something we want to do more about it, right? So we're thinking about, can we do like what's it, deep multitask learning? But this term actually have a paradox. The reason because if we're trying to do multitask learning, right? So typically when we say multitask learning, it's one of the key motivation is that the sample size is limited. Just like the sparse learning, right? So people really hear like sparse learning nowadays in this general imaging domain because they have a lot of data, right? So if you have less terabytes of data and you're trying to use this kind of complexity control type of method, you have to be you got to have a very good reason for doing that. But in general, you don't, right? So it has you don't have like a large sample size, and you're trying to use multitask learning, and then the other side of that is we're trying to use deep learning, right? But deep learning really says that we have to we need to have a lot of data before we can explore this kind of nonlinear interactions among the features, right? So combining this two actually is not that easy, right? So intuitively, it's not easy. But the good thing is that we can actually, we find a way where we're trying to build this networks layer by layer, and in each layer we're trying to do the same thing as this one layer. We're trying to sketching the subspace, and we're trying to do the same trick on the low rank space, in each layer of that, each layer of this network. And then once a layer is trained, it's never looking back. So you don't have to do this kind of end-to-end training, potentially expose yourself to a huge search space, and then this can actually give you a pretty good performance model, and then which comes with kind of nonlinear, can capture some of nonlinear information inside your data, and then you can still pretty good. And then that's what we call subspace network, and that's a work we have done a couple years ago, but we're still using that today because it's very fast, right? As I was saying, it's more like each time you train one layer and it's done, it's fixed, and you just do this, and of course we can, in the end, we can do the end-to-end fine-tuning if we have enough data. But if you don't, you don't have to do that. And then we validated, the conversions and subspace recovery is pretty good. And then, especially if we apply that into our problem itself, and we find out, in terms of predicting cognitive score, it can give you better performance than deep neural network, and also the simple multitask learning, and even, of course, the single task learning as well. And more than that, because we're building this network layer by layer, it comes with some kind of intuitive explanation of what are the things that are activated this layer, right? So so each layer, what kind of brain region are actually activating, and then trying to passing the information to next layer, and how this interaction are doing, we can actually easily to visualize that. All right, so this is the first work we've done, where we're trying to deal with the sparsity. We're trying to do this kind of nonlinear feature interactions using this multitask learning model. If you really come into the place where you want to use some kind of multitask model, we do have a package where we offer fairly online, where you can explore all kinds of more than 20 different methods, right? You can quickly try that. Okay, so and we even put a human in the loop for that, to learn this kind of task relationship, where we're gonna we're not going to talk about that today. So we could save the questions till later. So we have another session about. So we're going to continue talking about I'll say the meat of this talk. Sorry, Tim spent so much time, but I was told I have 1 hour, right? So I still have half of the time. So we that's as from imaging, right? And then nowadays we're doing more research on the digital markers, right? So when we're talking digital markers, what is the motivation of that? Typically when people find some severe memory issues, and if you go to the clinic, it's actually too late, right? So we want to collect more patients that's early phase, and then we're trying to discover the disease as early as possible. But unfortunately, right, so if you find any brain symptoms, right, to getting really bad is typically in the middle of the MCI, the later stage of MCI. So we want to have more people to know that something is going on very easily, very cost effectively, perhaps not go to any primary care physicians, just very easily to screen yourself against this dementia. And then how can we do that, right? So we find out, so the research question is that we have to do this kind of early detection, and that is affordable and accessible, right? And then this means that we don't want people just to visit your to visit a specialist before they can get assessed for that. And then we turn into different type of data sources. We turn into behavior markers where we have this kind of test bed where we set up all kinds of different sensors in the patient's home, where so we trying to collect the behavior, the working speed, and how much time you have the social time, you have this internet time, and your sleeping quality. And then we find out there's pretty much good amount of signals there, and then the signals is not overlapping with the brain signals as well. So we're talking about that in different talk if you're interested, but more we're talking about language markers, right? So this is all about this language markers. Is a couple of years ago when I was walking with my kid in the playground, and then we met this very old lady where we're trying to engage a conversation, right? So I say hi, and how are you doing, and then things should start to flow, but some exception happens. This old lady was talking about her home is not far away, and suddenly it's like talking about something else. So each individual sentence you hear is pretty much what's going on, but if you put the entire conversation together, that's pretty awful. You don't even know what's going on, right? It's like every sentence is more like disconnected from each other. It's pretty bad. So I was talking about to my collaborators in the OHSU, where she was conducting this kind of language study with Odin senior people, and then me and Dr. Wan and Dr. Hiroko Dodge were coming together saying, hey, can we maybe spend some time here in the conversation, and then can we see that if we can get some signal out of that. So we do since we have this kind of clinical trial going on, so we're having this kind of data moving forward, and we have this conversation data, and then we find out that simple ways we can simply just count some kind of keywords inside of the conversation, and then we actually can use very simple, let's say, I think we use support vector machine, and then we build this machine learning algorithm, and it's pretty good, right? So we have this kind of 72.5 kind of AUC on the patients, which is fantastic for this kind of MCI identification, right? Using imaging, you can do much better than that. And then so we start to think about what's going on here, right? So when people are talking about that, so the algorithm underlying thing is like, if you think about all the words and your syntactic structures, they're forming some kind of distribution, right? And we're saying that when you're talking about things, this distribution is starting to grow, and then if you talking infinite amount of thing and in infinite amount of time, and then this distribution will be a pretty stable distribution over there. And then what's make this algorithm to be successful is that this, I won't say algorithm, this study to be successful is that there are significant differences between the distribution of two type of between this normal cognitive normal subjects and the MCI subjects, right? So they have disease, so the way they speak actually different. So that's a good sign. So which means that if we talk to people enough, let's say for a long period of time, and then we can use what's inside the language to find out if this patient will have some early risk in Alzheimer's, right? But the thing is that this clinical trial is pretty time expensive, pretty costly. We typically need to engage the subject for 2 or 3 sessions, and each session we have 100 turns of conversation, right? So we ask questions and then they answer that, and have to a lot of turns, and then you collect enough kind of distribution information about the distribution where we can start to build the differentiation model. And then we're thinking about, can we actually do much better? Can we do better than that? Can we do let's say, can we maybe just ask a few key questions? Based on your answer, we can ask a few key questions, and then trying to find out the places that characterize these differences most within as short amount of time as possible, right? Can we do that? Can we sketch this distribution, right? Can we just we don't need a accurate distribution for doing this. We can just ask a few questions, right? If if I ask you one question and then you just start talking about your daily life, and then if I find out, maybe if I know more about how you talk about politics,